Everyone can see my screen. All right, let's get started. I think most people are here. Yeah. All right, let's get started. So this week we're going to do more probability. We're going to start with some practice problems, just kind of reviewing some concepts from last week, and then we'll get into other techniques for calculating probability. Before I get started, were there any questions from last week's lecture that anyone wants to ask? All right, if not, then let's get started. We'll just jump into some practice problems, and then after that, we'll start with some new concepts. So I picked a couple. These are all doable using the concepts that we learned last time. So basically, probability by counting or using combinations to count. And then basically, to calculate the probability of some event, we want to count the number of outcomes total and put that in the denominator, and then have the number of sort of desired outcomes and put that in the numerator. And then that is the probability that a desired outcome happens. So let's take a look at this just as review. So in this problem, it says each month in the country of Kaiser, so it's a fake country, residents wait until the first Thursday, then have festivals on every subsequent Tuesday until the end of the month. If a given month has 31 days, what is the probability that there are 4 festival days during that month? So let's take a look at a particular month. So let's just start the month as Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. So hypothetically, if the first of the month fell on a Sunday, then we would see, second is Monday, third is Tuesday, fourth is Wednesday, and so on, right? And then you would keep going. And what this problem is saying is if the month looks like that, then basically they wait until the first Thursday of the month, which is the 5th. And then every subsequent Tuesday until the end of the month, they have a festival. So I'll use a different color. So this is going to be a festival day, but the second would not be a festival day. And then if you keep going, this is going to be 15, 16, and 22, 23, and 30, 29, 30. So these would all be festival days. Does everyone understand the problem?
Miss Wendy, isn't
It
it Tuesday?
says on every subsequent Tuesday.
Oh, sorry.
So,
Yeah, you're right. Let's do this. So these would be the festival days. Did I do that correctly? Thanks for checking.
Yep.
Yeah. Okay. So in this case, I assume that the first day was Sunday, but that's only one possibility, right? The first day could be Monday, Tuesday, Wednesday, Thursday, Friday, or Saturday. And so it wants to basically have us calculate the probability that there are 4 festival days during this month. So any ideas on how we can calculate this?
Well, we can use the casework of the different starting dates for the month. So we'd have 7 cases from Sunday all the way to Saturday.
Yeah, okay, cool. We could do casework. So we already did Sunday, right? If the first of the month is Sunday, then we have 4 festivals, right? What about Monday?
Then we'll have 3 festival days
Why is that?
because the number of days in the month are 31, not 32. So if you shift it, you get 3 festival days.
Actually, it will be 4 because you're shifting to the right, not to the left.
Yeah, so let me just take another color so I don't have to redraw this calendar. But if you imagine the first is here instead, then basically you're gonna see this. And this is gonna be 18, oh sorry, 16, 23, 30, and the 31st is gonna be a Wednesday. So we're actually gonna have 4 festival days. Yeah, that's right. Okay, so let me undo that so we can reuse this calendar. But yeah, so Monday we'll have 4 festivals. What if the first day is a Tuesday?
I think that would
Still
also be
4.
4.
Mm-hmm. Wednesday?
Yep, still 4.
All right. Thursday?
4.
Okay. What about Friday?
Yes, still 4.
3.
So I guess someone who said 3, do you want to explain why 3?
Sure. So it says in the problem that they have to wait until the first Thursday until like they start doing the festivals on Tuesday. So since it would be on Friday, then like the next week they would have to wait until Thursday to go, and then there will only be 3 Tuesdays left after that.
Yeah, that's right. So I'm gonna just use the orange to show that. So basically, if the first day is a Friday, actually, instead of using orange, let me just write a new calendar. It might be easier to see. So if the first day is a Friday, the calendar is going to look something like this. And I'm not going to write down all the numbers, but basically you have 10, 17, 24, and then 31 here. And then this is going to be 11, 12, 18, 19, 25, 26, and so on. So the first Thursday is going to be the 7th, and then the festival days are going to be every Tuesday afterwards. So there's actually only 3 in this case. And then finally, what if the first day is a Saturday?
So not 3, yeah.
Yeah, it's going to be 3 as well. And you can see that by looking at this orange. Basically, if the first day shifts to Saturday, we're going to have the same thing. The 31st is going to land on a Monday. And so there's only going to be 3 festival Tuesdays. Cool. So now we've counted all the possibilities, right? There's 7 total. And then out of those 7, 5 of them will result in 4 festival days. So that's our probability. Any questions on this problem? All right, let's do a couple more. So this is a different question. It says 12 fair dice are rolled. What is the probability that the product of the numbers on the top faces is prime? So there's a lot going on here. There's a little bit of number theory and there's probability. So let's remember, what does it mean for a number to be prime?
It has factors of 1 in itself.
Right, so the only factors are 1 in itself. And so if we roll 12 dice, so remember one die can be 1, 2, 3, 4, 5, or 6. Those are the only possibilities for a die. Fair means the probability for each face is 1/6. So if I roll 12 of them and we multiply all the numbers together, how can I get a prime number?
It would have to be 11 of the numbers would have to be 1. Sorry, 11 of the dice would have to land on with 1 facing up. And then it would be either 2, 3, or 5 for the remaining dice.
Yeah. Does everyone see why that's the case?
Yeah.
Cool. So that's the only possibility. And so if we want to calculate the product or the probability of this, we want to count the total number of possibilities in each case. So remember, probability product is prime. We want to count number of sort of possibilities that 11 rolls are 1, and that 1 roll is 2, 3, or 5. And then over the total number of possibilities. Cool. So let's count the bottom first. How many total kind of different ways can I roll 12 die?
6 to the power of 12.
Right, yeah. So it's going to be 6 to the power of 12. You can think about this as like I'm rolling 12 different die, and then for each one, I can have 6 possibilities. And then what about the top? So we want to count the number of possibilities where 11 rolls are 1, and then one of the rolls is 2, 3, or 5. How many ways are there to do this?
Well, the position of the dice matters in this one. Like, the third dice is 5, and then all the other dice are 1, or is it just possible?
Yeah, that's a great question. So when we're looking at the denominator, we decided that the order matters. So if the order matters in the denominator, then we have to make the order matter in the numerator.
Okay.
So if the order matters, right, we can think of it as like we have 12 die, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? The order matters. We decided there were 6 to the 12 sequences possible for the denominator. And then we want to count how many sequences exist where there's 11 of them are 1s, and then one of them is 2, 3, or 5. So how do we count that?
Wouldn't it be 12 to the 12 cubed?
Why is that?
Well, because essentially the way it's arranged is that there will only be one number in one specific position each time. And that number can take up 12 different positions. And it's the same for 2, 3, and 5. They can each have 12 different positions in our line of dice. So you multiply the 12 different positions by the 12 different positions of the other ones to get 12 cubed.
I see. That's close. So you have the right idea. So there's 12 possibilities for the roll to not be 1. So we want to include the 12. But once we've picked what position that is, there's actually only 3 cases, right? That could be 2, 3, or 5. And so you can see this. So in this case, it's actually going to be 12 times 3. You could see this by trying like a smaller example. So for example, say you were rolling 3 die, and you wanted 2 of them to be 1 and 1 of them to be 2, 3, or 5. then basically you can choose one of them to be the 2, 3, or 5. So there's 3 possibilities. And then once you pick that spot, like say you pick this spot, there's 3 possibilities for that. It could be 2. I guess 3 is a bad example because it's 3 times 3. Let's say there's 4. So there's 4. So say you have to roll 4 die, and you want exactly one of them to be 2, 3, or 5, and the rest are 1. So there's 4 spots that you could pick the one to be. That's 4 spots where you could pick the roll that's not a 1, and then for that spot there's 3 choices. And you can see this by even like writing it out. And this is why it's 4 times 3 and not 4 times 4 times 4. So for example, if the first one is not a 1, then you can have 2, 1, 1, 1, 3, 1, 1, 1, 5, 1, 1, 1. If the second spot is not the 1, you can have 1, 2, 1, 1, 1, 3, 1, 1, 1, 5, 1, 1. If the third one is not a 1, then you can get 1, 1, 2, 1, 1, 1, 3, 1, 1, 1, 5, 1. And if the fourth one is not a 1, you can get 1, 1, 1, 2, 1, 1, 1, 3, 1, 1, 1, 5. So this is how you get the 4, right? The 4 is like there's 4 different spots, 1, 2, 3, 4, where you can put the roll that's not a 1, and then with each of these cases, it's times 3 because there's 3 possibilities. So in this case, it's kind of the same thing. It's going to be 12 times 3. Does that make sense?
Yes.
Cool. Yeah, you're super close though. It's the right idea. So for 12 times 3, we have that for the numerator, and then 6 to the 12th in the denominator. So now we can actually simplify this. So we can see there's actually a factor of 6 times 6 here. So this is going to be, so this is 6 squared. 1 over 6 to the 10. Any questions on this one?
No, please.
All right, one more, and then we'll move on to some new concepts. So here's another kind of uses a little bit of number theory. So I want to pick some examples where you kind of can see where probability and counting will intersect with some of the other math that you're learning in Matthew's classes. So this question says, find the probability that a randomly chosen positive divisor of 10 to the 99 is an integer multiple of 10 to the 88. So there's a lot of here, but first, do you all remember how we know if something is divisor of 10 to the 99, and how do we count how many divisors it has?
Well, you count how many divisors through prime factorization. Once you find the different powers of the different primes that make up the 10 to the power 99, you then go ahead and add 1 to each of the powers, the index value, and then multiply them against each other to get the total number of possible divisors.
Cool, yeah, that's right. So let's prime factorize this, right? So 10 to the 99, what's the prime factorization of 10 to the 99?
2 times 5 all to the 99.
Yeah, so that's 2 to the 99 times 5 to the 99. So let's look at our probability formula again. Probability divisor is multiple of 10 to the 88. That's going to be number of divisors that are a multiple of 10 to the 88 over number of divisors total. So let's calculate the denominator. What's the total number of divisors?
There's 10,000 divisors. So
Yeah, so how did you do that? Do you want to explain for everyone?
So when you add 1 to 99, it's 100. When you add 1 to the 99, that's the power of 5. It's also 100. So 100 times 100 is 10,000.
Right, awesome. So 100 times 100. And just as a review for people, it's 100 times 100 because you want to add 1 to each of these exponents. And the reason we want to do that is you can think of picking a divisor of 10 to the 99 as you want to pick some exponent for 2, you want to pick some exponent for 5 as a divisor, and then x can be anywhere from 0 to 99. So there's 100 choices for x. And then similarly, there's 100 choices for y. So to compute the total number of divisors, we want to multiply those together. So now let's tackle the numerator. So what does it mean for a number to be a multiple of 10 to the 88?
It means that it's divisible by 10 to the 88th power, but it also shares the same prime factorization as 10 to the.
Yeah, so we could write 10 to the 99 as 10 to the 88 times 10 to the 11, right? Which is 10 to the 88 times 2 to the 11 times 5 to the 11. And this is just kind of rewriting some stuff, but this will help us figure out how to count the number of divisors of 10 to the 99 that are multiples of 10 to the 88. So something divides 10 to the 99 if we can write it in the, something is a multiple of 10 to the 88 if we can write it in the form of some integer like k times 10 to the 88, where k is an integer. So any divisor will be a divisor of 10 to the 99 if we can write it in the form 10 to the sort of 2 to the some number between 0 and 99, and 5 to some number 0 to 99. And it's going to be a multiple of 10 to the 88 if we can write it in 2 to the something times 5 to something, where x, or where that something is at least 88 for both. So let me just write that down. So divisor, I'll say number if and only if, right, times 5 to the y. So this is just what we wrote above. But now we also want to see what it means for it to be a multiple of 99. So number, and then furthermore, D is a multiple Do these statements make sense to everyone? So basically, the first statement is if a number is a divisor of 10 to the 99, if and only if we can write it in the form 2 to the x times 5 to the y, where x is between 0 and 99, and y is between 0 and 99, inclusive. And that's sort of what we calculated before, and that's how we got there's 100 times 100 total divisors. Now, for D to be a multiple, this should be 10 to the 88. Then we basically need to know that 10 to the 88 divides D, which means 2 to the 88 divides D, and 5 to the 88 divides D. So the only way we can have that is if x is greater than or equal to 88 and y is greater than or equal to 88. So if we want to count the number of multiples of 10 to the 88 that also divide 10 to the 99, then we want to count the total number of numbers that satisfy this. Any questions so far?
No.
All right, so how many possibilities are there for D
20.
here? Why is that?
Because there's 11 possibilities for x and 11 possibilities for y. And actually, I want to change to 33 because you can have both x and y being possible values.
Yeah, so there's a couple pieces here. So first, how many possibilities are there for x and how many for y? So actually, since this is inclusive, right, it could be 88, 89, all the way to 99. How many numbers are in that sequence?
12.
Yeah, it's actually 12. So there's 12 possibilities for each. And then how do we count how many total combinations there are?
Wouldn't that be 144? 12 times 12.
Yeah, it's actually going to be 12 times 12. So the reason for that is there's 12 possibilities for x and there's 12 possibilities for y. So the total number of possibilities for some form 2 to the x times 5 to the y is going to be 12 times 12. And again, the intuition for this is you can try writing it out, but basically for each number of x, say x is 88, then y can be 12 different numbers. Y can be 88 or 89 or 90 or 91, etc. If x is 89, then we have the same thing, 88, 89, etc. So basically you're going to get 12 values for x, and then for each of those 12 values of x, there's 12 values of y, so you're going to multiply them together. So going back here, we've counted now there's 12 times 12 total divisors of 10 to the 99 that are multiples of 10 to the 88. And so we can simplify this. So it'll get us 9 over 25 squared, which is 9 over 625. Any questions?
No, please.
All right, cool. So now let's learn something a little bit new, basically another way for us to count probability now that we've reviewed counting directly. So this is a concept called complementary probability. And we can use an example to illustrate this, this concept. So let's say we have a problem that says, okay, there's a probability that it rains tomorrow in the city called Walla Walla, and the probability that it rains tomorrow is 7/10. What's the probability that it does not rain tomorrow?
3 out of 10.
Sorry?
3 out of 10.
3 out of 10. How did you get that?
Because if the probability that it's going to rain is 7 out of 10, and we know that probability is supposed to sum up to 1 when you add up all possible probabilities, so I just subtracted 7 out of 10 from 1.
Cool. Yeah, that's right. So, whoops. So the answer here is 3 out of 10. And let's see if we can generalize this idea, right? So if we have this set where the set will represent the total sort of set of outcomes, you can always divide that set into two parts that kind of make up that whole set. So for example, if you have the set U that's like 1 through 5 and a set A that's like 1, 3, and 5, then we can kind of take what we call the complement of the set, which is all the elements that are not in set A that are in the total universe of elements. So in this case, the complement of A inside U as the universal set is going to be 2 and 4, because those are the elements that are not in A. And basically we see that if we union both of them, basically we take all the elements in A and combine them with all the elements in the complement of A, then we get the total universal set. So we get all the numbers 1 through 5. And then the other thing around the complement is that it doesn't have any numbers in common with the set. So if we take 1, 3, and 5 and we intersect that with the complement of A, then there's no intersection. And this sort of 0 with a line through it represents the null set. So the set that has no elements. And so another way to say this is that when we union A and its complement, we get all the elements. And then if we intersect them, they have no intersection, so they're mutually exclusive. So that's a term you might see. Mutually exclusive means they have no elements in common. So we can apply this to probability because sometimes we have outcomes of events that fall into complementary categories. So in this case, it's very simple. Either it rains tomorrow or it doesn't. And in particular, for the mutually exclusive part, it can't both rain and not rain, right? It has to either rain or not rain. So if we union the possibilities where one possibility is it rains and the other possibility is it doesn't rain, then we get all possibilities. And then if we intersect those two, raining and not raining, then there's no overlap. So we have this mutually exclusive set where there's only two elements here, rain or not rain. And if that's the event, then we can basically have this realization that if we have these mutually exclusive events, then the probability that the event occurs plus the probability that the event does not occur is 1. And the only reason we can say that is because it's mutually exclusive and it includes all the possibilities. And then if we rearrange, we kind of see that the probability that some event does not occur equals 1 minus the probability that the event occurs. And we'll call this concept complementary probability because basically, like counting the complement, we're calculating the probability by calculating the complementary probability. So if we go back to this example of rain in Walla Walla, then let's say E is the event where it rains. So then the probability that E occurs, they said, is 7/10. So when we want to calculate the probability that does not rain, that equals probability it does not rain. And that equals 1 minus the probability it rains. And this is how we get 3/10. Oops. And so call this complementary probability. Does anyone have any questions about this overall concept? If not, we'll do some practice problems just to get a hang of it.
Ms. Wendy, I had a question. I wanted to know, in situations where you have multiple events, how would you solve to find one event if you, let's say you didn't have enough information to determine to just subtract from one?
Yeah, so you could basically apply this, right? It's still the same concept. It's just that the probability might be made out of multiple different events. So for example, let's say you have, actually I might have a good example of this in the practice problem. So yeah, okay, maybe we'll do an easier one. So say we're rolling a die and the die you know, again, you can roll 1, 2, 3. And the probability of rolling each one is 1/6. So we could basically kind of generalize this identity in a couple ways. But first, let's say we want to calculate the probability that you roll a 6. So the event is we roll a 6. Then the probability that we roll a 6 plus the probability that we don't roll a 6 is 1. And what that really means is probability of rolling a 6 plus probability of rolling not a 6 is 1. And what does it mean to roll not a 6? That actually is. Oh, go ahead. Go ahead.
Rolling a 1, 2, 3, 4, 5.
Yeah. So we roll 1, 2, 3, 4, 5. So this is like how we could generalize it for multiple events. Sometimes, so then if we have if your question is like, what is the probability that you do not roll a 6, you can kind of use complementary probability to say, okay, well, the probability I roll a 6 is 1/6. So the probability I roll not a 6 is 1 minus 1/6. You might also generalize this in other ways, like if it says, what's the probability that you don't roll a 2 or a 3? You can kind of say, okay, well, the probability I roll a 2 or a 3 plus the probability I don't roll a 2 or a 3 equals 1. This is, I would say, less useful when you're directly counting something like this, because you can very easily in this example directly count, okay, well, the probability I roll not a 6 is just 5/6. But this is actually very useful when you get to questions that maybe require where counting the complement is going to be easier than counting not the complement. So I can show some examples of that next, because in both of these examples, it's actually pretty easy just to think about like, okay, well, the probability, like I'm just going to count it. But let me show some examples where it's actually a lot easier to think about the complement. So let's do that. So this one, we're going to do all of them, but let's think about the last one first. So it says a fair coin is flipped 3 times. So let's skip over A and B right now. For C, find the probability that not all the results are heads and not all the results are. So if you were just given that problem, it would actually be like a little bit of effort to count, like, okay, what does it mean for not all the results to be heads and not all the results to be tails? So here's like one where I think using complementary counting is actually a lot easier. And so let's take a look at how we might do this. So we flip a fair coin 3 times. We have basically, for each coin, we can flip heads or we can flip tails. So for part A, it says, what's the probability that all the results are heads? How would you do this?
Since there are 2 probabilities, which is it will either be a head or a tail, it will be 1/2 all raised to the power 3.
Yeah.
Since you are flipping it twice.
Yeah, so basically, there's only one way to get all the results to be heads. It's going to be heads, heads, heads. And then there's 8 total possibilities, because for each one you can have heads or tails. So it's going to be 2 to the 3 third power in the denominator. So this answer is going to be that. So that's 1/8. What about part B? What's the probability that all are tails?
It's going to be the same as A, since they're just 2. So
yeah, so it's the same as A. So now we can solve C a little bit more easily, I think. using complementary probability. So it says find the probability that not all the results are heads and not all the results are tails. So how do we do this one?
So it will be 1 minus 1 over 8 plus 1 over 8.
Yeah. So, I mean, if you're subtracting 1 over 8 twice, right? So the way that we see this, we could do this is probability, not all results are heads, and not all results are tails. This equals 1 minus probability, all results are heads, or all results are tails. So this is the complementary part. And then we remember before we have this like probability rule of sums, right? Same idea as like the probability that something happens or something else happens. If those two things are independent, then we can basically write this as a sum. So probability, all results are heads, plus the probability that all results are tails. And then we just calculated that in part A and part B. So this is going to be 1 minus 1/8 plus 1/8. And this gives us 3/4. And to me, I think this is actually easier than trying to count the results directly. And similarly, if you were given the problem like a fair coin is flipped 3 times, how many sequences are there that are not all heads and not all tails? That's like a similar question that you might use complementary counting to count. Any questions on this one?
Okay.
All right, then let's do a couple slightly harder questions till we get the hang of it a bit more. So here's a similar question. This goes back to the earlier question about like, what if there's like, you know, a bunch of outcomes? So this one says a fair 6-sided die is rolled 4 times. Find the probability that at least 2 of the results are the same. So how can we use complementary probability to solve this one?
I think that we could start by finding out how many different outcomes there are.
Okay. How many different outcomes are there?
This is
This is the 4th.
Yeah. Cool. Okay. Let's go back to the numerator, or kind of calculating the outcomes. It wants us to calculate the probability that at least 2 of the results are the same. What's the complement of the event at least 2 of the results are the same? So let's say E is the event. What's going to be the complement, aka, or like i.e., you know, E does not occur? What does that mean?
That at most 4 results are different.
It means that all results have to be different, right? Or are you saying something else? Does this make sense to everyone?
Yeah.
Yes.
Cool. So now we can basically use our complementary probability. So the probability that E occurs plus the probability that E does not occur equals 1. So the probability that at least 2 results are the same equals 1 minus the probability that all results are different. And if we want to calculate the probability that all results are different, we already calculated the denominator, 6 to the 4 total outcomes. How many dice rolls, sequences of dice rolls are there where all 4 results are different?
I have 360.
How did you get that?
So basically, I sort of put down the placement, and I said that, okay, the first one has 6 options, the next one has 5, the next one has 4, and the next one has 3, and just multiply.
Cool. Yeah, that's right. So actually what I like to do is actually sometimes I don't multiply everything out in the numerator, and I don't multiply everything out in the denominator, and that actually makes it easier to simplify the fraction. So if I don't multiply this out quite yet, I can see, okay, I can cancel this out. This gives me 6 to the 3rd. I can also cancel this out, and this gives me 6 squared. So this is going to be 1 minus 10 over 36, which is 1 minus 5 over 18, which is 13 over 18. And this is another case where if we want to count directly, at least 2 results are the same. Usually it might be something like casework. We might have to count like, okay, what if 2 results are the same? What if 3 results are the same? What if all results are the same? And then we divide that by the total number of outcomes. And you can do that, but it's going to be more work. So similar to the idea of complementary counting, here's an example where it's actually going to be less work if you count the complement. If we count the probability all results are different, we just have to count one case. And that makes the calculation a lot easier. Any questions on this problem?
No, please.
All right, let's do a couple more. So this one says 3 numbers are randomly selected with replacement from the set of integers 1 through 100 inclusive. What's the probability that the product of the 3 numbers selected will be even? So anyone have ideas on how to get started on this one?
You could start with the denominator, which would be I think 1,000,000.
That's true. I think in this case, when we want to calculate the probability of this, let's first think about like how we could write this in terms of complementary probability. Because I think that if you expand out the denominators, it might make it harder to simplify in the future. But yes, it's true. There's going to be 100 cubed total possibilities. What's the thing that we want to count in terms of probability, and then what's the complement probability?
We're looking for the probability that the product of the 3 numbers is odd.
Yeah. So awesome. So basically, only one of 2 things can happen. The product can be even or the product can be odd. So we can say the probability that product is even equals 1 minus the probability the product is odd. And does anyone see why it might be easier for us to calculate the probability that the product is odd compared to the the probability that the product is even?
Does it have to do with the fact that if we were to lay out and look at how odd and even numbers multiply to produce even and odd, there are fewer ways to get an odd number through multiplication?
Yeah, totally. So basically, if we get a even number, that means that at least one of the integers that we select is even. And that's a little bit harder to count because that means we have to count like, okay, what if one of the numbers is even? What if two of the numbers are even? What if three of the numbers are even? But if we want to calculate what is the probability that the product is odd, the only way for the product to be odd is if all three integers we select are odd. So we could say that equals And so how do we calculate the probability that we select three odd integers?
Well, if we were to divide 50, the 100 into odd and even numbers, we would know that there are 50 odd numbers. And since there are 50 odd numbers, it means that if we were to multiply, it'd be 50 times 50 times 50. So there's 50 cubed options.
Yeah. So basically, between 1 and 100 inclusive, half of the numbers are odd. So the probability that we select an odd number is 1/2. And so the probability that we select three odd numbers, since we're selecting with replacement, is just going to be 1/2 times 1/2 times 1/2. You can also say, yeah, it's going to be 50. I guess I just simplified it earlier, but you could say, okay, it's going to be 50 cubed over 100 cubed. And that's going to be 1/2 cubed. The other way you can think about it is a probability that we select. We could say that's also equal to 1 probability that we select one odd integer cubed, which is 1 minus 1/2 cubed. So there's different ways you can count this. And then this is going to give us 1 minus 1/8, which is going to give us 7/8. And again, we can see that this problem, you can count directly how many ways are there to select even numbers. But here's another case where you probably end up using casework to count, how many different ways can I select three numbers where like one number is even, or two numbers are even, or three numbers are even. And so it's going to be simpler for us to count the complements. Any questions on this? All right, let's do one more. So it says a bag of 20 marbles. There's 5 red, 5 green, 5 blue, and 5 yellow marbles. Then we pick 4 marbles, randomly selected without replacement. What's the probability that 2 or more marbles are the same color? So how can we use the complementary probability idea here?
The probability that none of them are the same color.
Yeah. So probability 2 marbles are the same color. 1 minus probability that all marbles are, 2 or more marbles are the same color, equals 1 minus the probability that all marbles are different colors. And again, kind of the intuition for why we might want to do it this way is, first we might think, okay, let's just count the probability that 2 or more marbles are the same color. And thinking about that, my intuition says, okay, we probably have to do casework, right? And the cases are going to be 2 marbles are the same color, 3 marbles are the same color, and 4 marbles are the same color. And so we're going to have to count like different cases and make sure that we're only counting everything exactly once. But here, if I think about the complemented, there's only one case where all marbles are different colors. it's when I have exactly one red marble, exactly one green marble, exactly one blue marble, and exactly one yellow marble. So when it's easier, again, like you think about counting the calculating the main probability and calculating the complement probability, here it's going to be easier to calculate the complement. So how do we calculate the probability that all marbles are different colors?
Would it be 20 choose 4 because we're choosing 4 marbles out of 20?
So 20 choose 4 would be, that's how many different ways you could choose 4 marbles. But here here we have a couple complications. The first one is that we have we have multiples of the same color of marbles, right? So 20 choose 4 would work if we had 20 different colors and we want to pick 4 of them. The order doesn't matter.
Okay. Then could it be 20 to the 4th power?
So you're close. So here we can maybe, to make things easier, let's assume that we're like picking marbles in order. So first we pick a color and a marble, then we pick another, then we pick another, then we pick another. And it says we want to select it without replacement, which means once we pick a marble, we don't put it back. So for the first choice, in the denominator, we have 20 total choices because we can pick, one of any of them. For the second one, we have 19 choices, then 18, and then 17. Does that make sense?
Yes, please.
I'm kind of lost because the first one there would be 20 marbles to choose, but the second one, since you've already chosen a color for the first one, wouldn't the number of marbles that you could pick to get different color from that be 15?
Yeah, so that's the numerator. So let's first, let me write this down. So this is going to be a number of ways to choose 4 different colors over the number of ways to choose 4 marbles. And so we're just calculating the bottom here. So that's going to be 20 times 19 times 18 times 17. And then the numerator, you're right. So if we want to choose 4 different colors, for the first marble, we can choose any of them, right? But now for the second marble, if we want to choose something that's a different color, there's only 15 that we could choose. That would be a different color, right? And so can you repeat what the top would be?
Then 10, and then 5.
Yeah. So let's calculate what this is. We can simplify this by canceling here. We can also cancel here.
2 from 18, yeah.
Right. So the top is going to be 125. And then the bottom, what's it going to be? So I want to calculate it. I think it's 969.
Yep, 969.
And then this is going to give us 844 over 969. So this is one way we could count the complement. I know at the beginning someone said you could do 20 choose 4 ways to select 4 of the 20 marbles. And so I want to also call out like a solution where you could use that fact. So in this case, we're basically counting the probability by kind of assuming that order matters in the denominator and order matters in the numerator. If we want to do 20 choose 4, what we're basically saying is we want to select 4 marbles, and the order of selecting the marbles doesn't matter. And so here we could do 20 choose 4. And then when we count the numerator, we'd want to say, how many ways can we select 1 marble of each color? So instead of saying at the beginning, there's like 20 different ways, we can actually just pick 1 of the 5 for each color. So we can basically pick 1 of the red ones, 1 of the blue ones, 1 of the yellow ones, and 1 of the green ones. And for each of them, there's like 5 that we could pick from. And actually, this is going to give us the same number. If you simplify it, you give. You kind of would simplify it the same way to get 969, which would give you the same number. And I think the key here is just making sure that you count sort of the top in a consistent way that you count from the bottom. So here when I'm saying number of ways to choose 4 different colors, I'm also saying in order. But here where I'm saying order doesn't matter. But the individual marbles matter. And as long as we're counting the top consistently with the way that we count the bottom, the probability will still turn out the same. Any questions? So a couple takeaways on the casework thing. I think one sign to potentially, on the complementary probability thing, one sign is when you might end up doing a lot of casework. That's when you want to basically see, hey, is it easier to do this using complementary probability? One thing that you might see is like when there's at least something, or when there's 2 or more of something, that usually means, hey, I need to do cases to count, like what if it's 2, what if it's 3, what if it's 4? And then that can be sort of an indicator in the problem that you might want to use complementary probability. And so if we revisit some of these problems, we see like, in this one it says at least 2 of the results are the same, or this one says what's probably, oh, this one's different, but this one's like that 2 or more are the same. And so that's kind of a hint that you might want to use complementary probability. Of course, it's not going to be exact. It's not like every time you see that, that's going to be the answer, and every time you don't see that, you don't want to use it. But it could be something to think about. All right, any questions before we move on?
No, please.
All right. Cool. So I want to move on to another type of probability. And this is kind of using geometry to help us calculate probability. So sometimes we can count sort of the total number of possibilities of an event, but sometimes we can't. Sometimes we have infinitely number of possibilities. So if the question is like, let's select a point, you can basically pick any infinite number of points. And so many of these problems, you can't solve it by counting how many points there are and counting how many points you might want to select. So instead of counting discrete numbers, you might actually have to solve this by comparing lengths or areas or volumes instead of counting. So let's look at an example. Here it says a point is selected at random between 0 and 10 on the number line. Find the probability that the point is closer to 2 than to 4 on the number line. So easiest way to visualize this would be, let's actually draw a number line. And let's say we start at 0 here. 1, 2, 3, 6, 7, 8, 9, 10. So which parts of the number line are closer to 2 than to 4? I won't show the answer yet.
Numbers less than or equal to 2. Sorry,
Okay.
numbers less than or equal to 3.
Yeah, so any number that's kind of at this point or this way is closer to 2 than it is to 4. And then any number that's kind of on this side is closer to 4 than it is to 2. And so we can also, reason this through. Anything that's less than 2 is obviously closer to 2. Anything that's greater than 4 is obviously closer to 4. And then if we look at anything other than 3, which is equidistant from 2 to 4, anything between 2 to 3 is closer to 2, and anything between 3 to 4 is closer to 4. So the way that we could calculate the probability that the point is closer to 2 than to 4 is by actually computing the lengths of these segments. And again, like you can see that if we want to apply our old principle of counting, how many different points could I pick, we wouldn't be able to solve it because we can pick sort of any infinite number of points here. And so when there's infinitely many possible outcomes of an event, we can basically look at this like the size of each area where there's a successful event over the size of the total area. So it's basically this formula here. So let's take a look at our problem. So if we want to count the size of the segment where the points are closer to 2, we're going to look at basically this segment here from 0 to 3. So what's the length of that segment?
3.
3.
Yeah. And then the total length is from 0 to 10 because that's the total possibility. What's the length of that?
10.
Yeah, not a trick question. So here it's just written out, but basically then we know the probability is closer to 2 than to 4. We have the size of the successful region, which is basically 0 to 3, and this is 0 to 10. So the length is 3 over 10, so you get 3/10. Any questions about this example? Does that make sense?
No, please.
Cool. So this is a pretty simple example, but I do want to note that with some problems, region sizes are going to be lengths, but sometimes it could be areas or volumes or kind of sizes of spaces in general. And so depending on the problem, you might have to be calculating different sizes. And as you're becoming familiar with geometric probability, a good exercise is kind of identify the number of variables necessary to solve a problem. And that can help you with the dimension of the geometric regions you need to compare. So for example, in this case, we're just picking one point on a line, so there's only one dimension. But say you need like 2 variables, then that might be more of an area type thing. So that's a 2D thing. Or if there's 3 variables, you might be comparing volumes. So we can do some examples to get more familiar with this idea too. So I picked some over here with some room to do it. First, we'll start with a line. So here is a similar question. A point is randomly chosen on a line segment of length 10 units. The segment is then broken into 2 pieces at that point. Find the probability that the longer piece is at least 3 times as long as the shorter piece. So I'm going to take a look at this. So we have a line segment. This is 10 units total. Then we pick some point on the line segment. We divide that into 2 different line segments. And the problem wants us to calculate the probability that the longer piece, in this case, this one, is at least 3 times as long as this piece. So when will that happen? Any ideas?
It'd have to be so, happen in a way so that, yeah, the number we're adding is, when we add it to the shorter piece and the long piece, we'll get 10. So pairs that sum to 10.
It does have to sum to 10. But when is it going to be the case that the longer piece is 3 times the length, at least 3 times the length of the shorter piece? So
if that point, sorry, if the shorter length is less than or equal to 2.5, which is 10 divided by 4.
Yeah. So that's right. There's a couple ways you can get to that, right? I think one is you can kind of guess and check or kind of think about intuitively. If the longer piece is at least 3 times as long, then like it will divide at the 1/4 mark. So 10 over 4 is 2.5. Another way you could do this that's a little bit more systematic is let's say we draw the point at some point where the distance from the left side to that point is x. And then as the first person said, this needs to sum to 10. So the length of this one needs to be 10 minus x. And so if we want to express algebraically that the longer piece is at least 3 times as long as the shorter piece, then that would happen if, like say x, 10 minus x is a longer piece, and that means it's at least as long as 3 times the shorter piece. Or maybe x is the longest one, and that means x is at least 3 times 10 minus x. So either of these would result in the longer piece being at least 3 times as long as the shorter piece. So now we can solve for x. In this first case, we get 10 is greater than or equal to 4x, or x is less than or equal to 2.5, which maps to basically if this is at 2.5, then if I pick any x in this, or any point in this region, and then divide it up, that means the longer region is going to be at least 3 times as long as the shorter one. In the second case, if I have x is greater than or equal to 3 times 10 minus x, then I can solve for x. That gives me, I'll write down here, x is greater than or equal to 30 minus 3x, which means that 4x is greater than or equal to 30, which means that x is greater than or equal to 30 over 4, which is 7.5. So this is the case where this is 7.5. I pick something in this region. And again, you can kind of also see when you draw it out that if I pick some point here, then the longer segment is going to be more than 3 times the shorter segment. So now let's put this together to compute the probability. So what's the length of each of these intervals? And then how do we compute the probability overall that the longer piece is at least 3 times as long as the shorter piece?
It would be 2.5 over 10. And since 2.5 is this is a quarter of 10, we'd say it's 1/4.
Yeah, so the probability is 1/4 that x is the shorter piece and the longer piece is at least 3 times as long as the shorter piece. But it's also 1/4 that x is the longer piece and the longer piece is at least 3 times as long as the shorter piece. So we need to count both of these cases. So we could do this a couple ways. First, we could say, okay, the probability of this one is 1/4 and the probability of this one is 1/4. And we add them, so the total is 1/2. Or we can say, okay, what's the total length? And the total length here is 2.5. The total length here is 2.5. So we get 2.5 plus 2.5 over the total length is 10. So this gives us 5 over 10, which is 1/2. So kind of putting these two together, we get that, you know, if I'm picking a point is randomly chosen on line segment of length 10, then basically what that means is it's called the 0, 10. If I pick any point within this region or this region, then I'm gonna get the condition where the longer piece is at least 3 times as long as the shorter piece. And so we can calculate this by calculating the total length, which is 10, and the total highlighted length, which is 2.5 plus 2.5. Any other questions?
No, please.
Cool. Let's try something different. So here's a different problem. It says if x is between 2 and 6 inclusive and y is between 3 and 6 inclusive, find the probability that x plus y is less than or equal to 9. So any ideas on what would you do if you saw this problem?
I would start by trying to find the different values for x and y.
Yeah, we could try some things out. We could see, okay, well, you know, x plus y, you know, if we pick like x is 2 and y is 6, that would work. If we pick like x is 6, y is 5, that wouldn't work. So we could try some stuff out. But here, I think it's also going to be hard to directly count the probability because there's sort of an infinite number of options, right? Because x could also be a decimal. It could be, you know, 2.5 or 2.55. So when you see something like this, it's another clue that we might want to compute areas. So what I would suggest when you see a problem like this is actually, let's like draw something out and see what we can see from the graph. And so here, instead of it being on a line, because we have 2 variables, we actually want to draw in 2 a coordinate system with 2 axes. So let's have x and y on these axes. And we can draw out first, let's first draw out like what these mean. So if 2 is less than or equal to x and x is less than or equal to 6, then what does that look like in the plane? So it basically means that x is between 2 and 6, and then y is between 3 and 6. So that means we're picking a point within this rectangle. Does everyone see what that is?
Yes, please.
What's the area of this rectangle?
Will it be
Well,
3?
12 units squared.
Yeah, do you want to explain why for everyone?
Because the x-axis, the I don't know, the difference between the two is 4, and for the y-axis, the difference is 3. So that gives you the length of the rectangle. And to find the area of a rectangle is length times breadth. So
Yeah, so this is at 3, this is at 6. So sort of the height of this rectangle is 3, and the width of the rectangle is 4. So the area of the rectangle is 3 times 4, which is 12. Cool. So now we want to see when does x plus y, when is it true that x plus y is less than or equal to 9? So I think the easiest way to see this would be to actually graph the inequality x plus y is less than or equal to 9. So does anyone want to explain how they would graph this? So use a different color. So how do you graph this?
we could maybe make it x minus 9 equals y.
Okay. So it's actually not going to be equals, right? It's going to be y is less than or equal to negative x plus 9. Does that make sense?
Yeah.
Okay. Yeah, so if we want to graph this, we basically would graph the line, right? Y equals negative x plus 9, and then we would kind of find which side of the line satisfies this inequality. So here, the y-intercept is 9, so maybe I'll draw 6, 7, 8, 9. And then the slope is negative 1. So basically, it's going to be a line that goes through these points. I'm going to try my best to draw this straight. So this is x plus y. And so which side of the line represents the side where x plus y is less than or equal to 9?
The part within the rectangle.
Well, there's two parts within the rectangle, right? There's this part and this part. This part and this part. So which side is going to be the side that satisfies x plus y is less than or equal to 9?
I think the side to the left.
Yeah, so remember if we were to graph if we were to graph y is less, if we were to graph this or this, right, these are the same, you would graph like so. And then the less than or equal to part would be this side. So in this case, if we have these constraints, then the area that we really want to be calculating is this area right here. Any point in this green region is going to satisfy x is between 2 and 6, y is between 3 and 6, and x plus y is less than or equal to 9. Does that make sense to everyone? Does anyone have any questions?
Yes, please.
All right. So then let's go back to this problem, right? We want the probability that this happens. And so here we want to compute, again, the size of each region. So we want to compute the size of the successful region, which would be in this green area, over the size of the total region, sorry, which would be the rectangle. So so let me write this down. Probability that x plus y is less than or equal to 9 if equals area of, in this case, it's the green region, over the area of the orange rectangle. Because the orange rectangle represents all the total points that we could be picking, with the constraints 2 is less than or equal to x is less than or equal to 6, and 3 is less than or equal to y is less than or equal to 6. And the green region represents the portion of that where x plus y is less than or equal to 9. So how do we calculate the area of the green region? We already calculated the area of the orange region. That was 12.
The area of the green region. So we have to divide it into a triangle and a rectangle. The rectangle having a height of 3, and I think it's 2. The width would be 2, if I'm looking at it correctly. Yeah, 2.
Mm-hmm.
So the rectangle part of our area is 6, and then we have another 2 as our.
Excuse me, sorry to cut in, but it will actually be 1, not 2.
Yeah, I was trying to draw this
Yeah,
out.
because
I
6
think it
plus
doesn't
3
quite.
equals 9, not 4.
Yeah. So we could think about what point would be on this line, right? This line is the line x plus y equals 9. So if y is 6, then x has to be 3. So this is 3 comma 6. Remember, this is 2 comma 6. But you're close. So whoever was talking earlier, you were talking about then we need to calculate the area of the triangle. So how do we calculate that?
So the area of the triangle is the half the height times base. We know the height is 3. We know the base is 6 minus 3. So 3. So 3 times 3 is 9. Half of 9 is 4.5. So 4.5 plus the 3 for the rectangle is 7.5.
Yeah, so here you have this area is 3, and this area was 9 halves, which is 4.5. So this is 7.5 over 12, which is the same as
3
15
out of 8.
over 24, which is, it's 5/8.
Sorry, I meant 5.
Yeah. Any questions? this problem. So this shows how we could kind of generalize what we did on a number line to multiple variables. All right, let's try a different problem. So this is, again, there's two variables here. So here's a point x comma y is randomly picked from inside the rectangle with vertices 0, 0, 4, 0, 4, 1, and 0, 1. What's the probability that x is less than y? So any volunteers to walk me through the problem?
I think to start, you want to graph this.
Okay, let's do it. Let me graph. Okay, what should I graph? The vertices?
Yes.
Okay, so 0, 0, 4, 0, 4, 1 is over here. And 0, 1 is over here. All right, so I've graphed this, and let me maybe use, I'll use orange again. To draw the rectangle. Cool, I've graphed the rectangle. What's next?
We would create a formula for a line that would pass through these points. I was thinking it could be x plus 4 since the greatest x value is 4. So x plus 4 equals y.
So let's go back. So in this case, the constraint is x is less than y. So we actually want to plot this line. So x is less than y looks something like this. So this is the line x equals y. And if we want x to be less than y, which side of the line does it need to be on?
The left side.
Yeah, it needs to be on the left side. So I guess in this case, let me just draw it as a dotted line because we know it's so this is x equals y. And then for it to be less than y, it basically needs to be in this region over here. Because anything over here is x is less than y. Does that make sense?
Yes, please.
All right, so how do we calculate the probability?
So once again, it's the area of our chosen region over the area of the total region. The width of the total region is 4, its height is 1. So it has an area of 4 units squared. Yeah, the triangle that we're using has a height of 1 and a base width of 1. So 1 times 1 over 2, that's 0.5 over 4.
Cool. So this gives us 1/8. Any questions on this one? Cool.
What is the area for the Sorry, for the triangle 1. Sorry, 0.5.
So we could look at the triangle as, so here, let me just blow it up maybe. So the triangle has this shape, right? And this length is 1 and this length is 1. Furthermore, this is a right angle because we know this is the angle of a triangle. So the area is 1/2 times base times height. And if we view this as the base and this times the height, it's going to be 1/2 times 1 times 1, which is 1/2.
Okay, thanks.
Yeah, no problem. Intuitively, you can also think of it as like kind of you complete a square to make a triangle. And the area of the square is 1 because it's 1 times 1. And then the area of the triangle is half of it. Cool. So picked a slightly trickier one next. So this one says a point E is chosen at random from within square ABCD. What is the probability that ABE, the triangle ABE, is obtuse? So there's a little bit of like different geometry terms here. Can anyone remind us what it means for a triangle to be obtuse?
Yeah, it means that it's greater than 90 but less than 180 degrees.
Yeah, so it means that one of the angles is greater than 90 degrees. So go ahead, someone have a question? Okay, so just an example, right? This would be an acute triangle because all the angles are less than 90 degrees. But this would be an obtuse triangle because this angle is greater than 90 degrees. So let's draw out this question, right? So we have a square ABCD. Let's just label it A, B, C, D. And then it says we choose some point E. And then we draw a triangle ABE. And then it says, what's the probability that this triangle is obtuse? So when would A, B, and E make an obtuse triangle?
If E was closer to if E was between the center of this square and the middle of line AB, like on that line.
Yeah, that's true. So if E lies kind of over here, then it's going to be obtuse. Oops, that's a bad line. This would be obtuse, right? That totally makes sense. So one thing to note here that's very useful is if I have a circle, it's going to feel a bit like a side note, but and then I have, you know, this is the diameter of the circle, and then I pick any other point on the circle. Does anyone know what this angle would be over here?
Leave it 30 degrees.
So I guess this is a useful property, but basically if I pick any point on the circle, then this is actually going to be 90 degrees. And I guess you could see this in a couple of ways. But for example, if you take the middle, right, this is going to be isosceles right triangle. But if you take any other point on the circle, it's still going to give you 90 degrees. And this is a really useful fact that will help us solve this problem. Is this something that you learned in the geometry lesson yet?
No.
Okay. So let's, I guess, maybe take a side note. We could, let me explain why this is the case. So this is the diameter, so we can divide that into like a radius. The length is a radius and this is a radius, right? And then furthermore, since this is a point on the circle, this is also, let me first remove this mark. We haven't proven yet. This is also length r. That makes sense, right? So this length equals this length equals this length. And let me just start labeling some of these points. So I'll call this O. Let me call this X, Y, Z. So we have a triangle X, O, Y. This is an isosceles triangle. Do y'all know what an isosceles triangle is?
Yes.
And then do you see why this is an isosceles triangle?
Yes.
Yes.
Cool. Spelled it wrong. Isosceles. And then similarly, we have triangle YOZ. It's also isosceles because this length equals this length. Oh, sorry. OY equals OZ, right? Because they're all radii. And then what we know about isosceles triangles is that the angles are equal. So this angle equals this angle, right? And then I'll use a different color. This angle equals this angle. Does everyone see why that's the case?
Yes, please.
Cool. So let's just call the blue one, we can call it, here, let me go back. So let's say the green angle, let's call this value B. And then the blue angle, let's call this value A. Then what we have is, let's look at triangle XYZ. So what do we know about the sum of the angles in a triangle?
They equal 180 degrees.
Right, yeah. So sum of the angles of XYZ, angle X plus angle Y plus angle Z equals 180 degrees. And then we know angle X, right, is just this blue angle that we called A. Angle Y is actually the sum of this blue angle plus the sum of this green angle. So we'll call this A plus B. And then angle Z is just the green angle, so it's B. And this is 180. Any questions about that step? All right, and we don't have to solve for A and B because, you know, we just picked an arbitrary point. A and B could be anything, but we can note that we could rearrange this as 2 times A plus B equals 180. Does someone have a question? All right. And then if we divide both sides by 2, then we see that A plus B equals 90. And then remember, angle Y was A plus B. So angle XYZ equals 90. So this proves that this is a right triangle right here. Did everyone follow along? Were there any questions about this? I know it's not directly probability, but it's super useful geometry fact, and then we're going to use it to calculate this probability. Makes sense? All right, so let's go back to our problem. So we have a circle. Now we have this fact that, I'll draw it again here. Now we have a fact that whenever we have a circle, any point on the circle will give us a 90-degree triangle. Any point sort of outside the circle is going to give us a less than 90-degree angle here. And then any point that's kind of inside the circle is going to give us a greater than 90-degree. So it's going to be obtuse. Does that make sense?
Yes, please.
And you could see this in a couple ways, right? Like one way would be, say I pick any point outside the triangle, then I can draw the line from the center, outside the circle. I can draw the line from the center of the circle to that point outside the triangle. And then I can, connect these points. And since we know this angle is 90, then this angle must be less than 90. And the reason for that is we could look at this angle plus this angle has to equal 90, and this has to sum to 180. At the same time, this angle plus this angle over here, and this angle plus this angle over here, that means those two angles is greater than 90, since this angle, let me just label them. It's called A, B, C, D. Since A plus B equals 90, then A plus B plus C plus D is greater than 90, which means that this angle over here has to be less than 90. Now let's look at the case where it's inside the circle. So if I pick a point inside the circle, let's say this point over here, I can do a similar thing. I can draw the line through that point, and then it hits the circle somewhere. I can draw this triangle over here. Try my best here. Draw this point over here. This is 90 degrees. And then I can draw this triangle over here. And again, we can say label these angles A, B, C, D. So then we know A plus B plus C plus D equals 90 because of what we just proved, which means A plus C is less than 90. So this angle over here must be greater than 90, so it's obtuse. Does that make sense to everyone?
Yeah.
Yes.
Cool. So now let's go back to this problem. We want to see when is A, B, and some other point E, when does that form an obtuse triangle? So we can use what we learned here and draw the sort of circle with AB as the diameter. And it's going to look like this. Something like that. I'm drawing this freehand. And we only care about the points within the square ABCD. So that means we don't really care about this side over here. So let me just erase it. We don't really care about this side. Now, with those facts that we learned, when is ABE obtuse?
When the
If
E
E is in
doesn't
that
cross the diameter.
semicircle.
Yeah, so if E is within this circle, then it's going to be obtuse. If E is on the circle, then it's going to be a right triangle. And if E is outside the circle, basically in this region, then it's going to be acute. So triangle ABE is obtuse if E, if and only if E is within the shaded area. This is if E is a point in ABCD. So this is what we've sort of derived or concluded. All right, so now we want to calculate the probability that E is in the shaded area, right? So the probability that ABE is obtuse, we've reduced this into probability E is in the shaded area. How do we calculate this probability?
Well, we first have to assign a value to the sides of A, B, C, D, like for two,
Okay.
just
Okay,
two.
sure, let's say they're 2.
So the area of the square is, the total area is 4. And we know that the shaded region is a semicircle. So we're going to use half of the original formula. So it's going to be pi r squared, which is just pi. Pi over 2 is the answer.
Right, so we have that the formula for area of a circle is pi r squared. In this case, we have half the circle, so it's 1/2 pi r squared. In this case, the radius is 1, so it's just going to be pi over 2. So the total probability is pi over 8. Any questions on this problem?
No, please.
All right, let's see if we have, I think we have time to do one more. Let's do this one. So this one says 2 points on the circumference of a circle are of radius r are selected independently and at random. From each point, a chord of length r is drawn in a clockwise direction. What is the probability that the 2 chords intersect? So there's some key terms here. Does anyone know what a chord of a circle is?
It's a
Yes.
line segment from one point on the circumference of a circle to another point on the circumference.
Yeah, that's right. So let's draw this out. So we have a circle of radius r. So let me just draw a circle as best as I can. And the radius is r. And then it says we pick 2 points independently and at random, and then we draw a chord of length r in a clockwise direction. So what that means is, say I pick this point, then I'm going to draw a chord of length r in a clockwise direction. And say I pick some other point, let's say this point, then I draw another chord clockwise direction of length r. What is the probability that 2 chords intersect? So in this case, that they would intersect, but it's also possible, say I pick a chord over here and I draw it, that it doesn't intersect. So any ideas on how we could do this problem?
Well, from what I can tell, it's that it's limited to the area of the radius for the chords. For example, since that point is not since the point that we've just picked is not part of the radius. And if we pick another point and it's, no, I think I'm confusing myself.
Yeah, I see what you're saying. It's close. So basically, we can suppose that we pick some, first we pick some point. It doesn't really matter which point we pick. And then we draw this chord R. Then we want to see, okay, we want to pick a second point. What's the probability that it will intersect the first chord? And there's actually two ways that it could intersect. So the first is if it's along this chord, along this arc, then it will intersect. Let me use a different color. So if it's along, this one's hard to see. Let's use maybe orange. So if it's along this arc right here, then it will intersect. So if I pick like any point here, I'm going to get an intersection. The second option is if I pick something over here, I might intersect it as well. Because if I pick something over here, I might also draw something like this. So if you actually think about it, it's going to intersect if I pick anything along this arc over here, and the length here is R as well. Because if I pick this chord here, it will just intersect at this one point. If I pick anything closer, it will kind of overlap. And then if I pick anything farther, it's not going to intersect. Does that make sense to everyone?
Yes.
So basically, if I pick anything here, then it will intersect. And if I pick anything else on the circle, it will not. So now I want to calculate, what's the ratio of this part of the circle relative to the whole circle.
And will be 2 out of 6.
You want to explain why that is?
Because I know a hexagon's, the length of a hexagon's side, if regular hexagon side is the same as the length from the center to the to a vertex. So since the hexagon has 6 sides and this is basically 2, this will be 2 out of 6.
Yeah, that's a great explanation. So let me explain why that is too, right? So first, we know that these 2 points, say we have a chord of length R. We know these 2 are radii. So this is R, and this is R. And so here we have an equilateral triangle. And we know for an equilateral triangle, each of the angles is 60 degrees. And so for a circle, the circle is 360 degrees. So we actually have 6 of these equilateral triangles that make up a circle. And yeah, so this is where you get the regular hexagon as well. Sorry, my drawing's not perfect. It doesn't, some of them don't look like equilateral triangles, but if they were all, if the chord lengths were all R, then these are all 60 degrees, and then these are equilateral triangles. And so then this chord is 1/6 of the circle, and so 2 of these is actually 2/6, which is 1/3. Awesome. Any questions on this one?
No, please.
All right. I will post these notes in the handout. There's more questions for practice. I would recommend that you go through all the geometric probability questions. I think there's a couple more that we didn't get through, but they're really great. And just go through page 10 of the handout as homework, and I'll make a post about it as well. Thanks everyone for coming. I will see you at the end of the week for office hours.
Okay, thank you too. Bye.